So I promised you that the spectral theorem comes in 3 stages. We just stated and proved the first step of, or the first part of the spectral theorem, which says that the eigenvalues of any Hermitian matrix are guaranteed to be real numbers. Now let's move to the second part of the spectral theorem. This part says that the eigenspaces of a Hermitian matrix H are all orthogonal to one another. So I want to walk through the proof of this one as well, because I think it's pretty interesting. So here's how we're going to start. We're going to start with an eigenvector v1 corresponding to an eigenvalue lambda 1. And we're also going to have an eigenvector v2 corresponding to an eigenvalue lambda 2. And here we're assuming that lambda 1 is not the same as lambda 2. Our goal here is to argue that this arbitrary choice of 2 eigenvectors coming from 2 different eigenspaces are orthogonal to one another. So to argue that those 2 vectors are orthogonal, let's look at their inner product. The inner product of v1 with v2, well, we're going to use a trick that's quite common in math sometimes. And what we're going to do is we're going to multiply this inner product, v1 with v2, by 1. But when we choose 1, we're going to represent 1 as lambda 1 minus lambda 2 divided by lambda 1 minus lambda 2. And this is a legitimate expression here because part of our assumption is that these 2 eigenvalues, lambda 1 and lambda 2, are different, which means that the denominator of this expression is not equal to 0. Okay, so that's the first step. And now what we're going to do is we're going to push in the numerator of this, the way we've cleverly constructed 1 here, into the second slot of the inner product. So now we have the fraction 1 over lambda 1 minus lambda 2 multiplied by the inner product of v1 with the linear combination lambda 1 times v1 minus lambda 2 times v2. Okay, now what we're going to do is we're going to distribute the inner product across that across the linear combination in the second slot. So now we have 1 over our denominator, so our fraction here, multiplied by lambda 1 multiplied by the inner product of v1 with v2 minus the inner product of v1 with lambda 2 times v2. So we're pushing all these symbols around, and we're hoping that pushing them around will maybe jog something loose here. And indeed, I think we might see something useful, because part of this expression now is lambda 2 times v2. Well, we know that lambda 2 times v2 is the same thing as h times v2, because v2 came from the eigenspace of h, where the eigenvalue was lambda 2. Also, in this step, we are moving lambda 1 into the first slot of the inner product we're multiplying by, v1 inner product with v2. But when we move lambda 1 into that inner product, since we're moving it into the first slot, we have to conjugate lambda 1. So now we have our expression, and it's sort of, maybe part of it we're simplifying, but part of it isn't quite simplified. Well, now I want to point out that the first part of the spectral theorem says that lambda 1, since it's an eigenvalue, is a real number. So its conjugate has to equal itself. So now the conjugate of lambda 1 equals itself. And also, in the second term here, where I have the inner product of v1 with h times v2, the adjoint formula says I can move h to the left-hand side of that inner product as long as I take the conjugate transpose. But now there's even more simplification that occurs. For one, I know that lambda 1 times v1 is h times v1 because lambda 1 is an eigenvalue of h and v1 is a corresponding eigenvector. I also, on the right over here, know that h star equals h because part of the assumption in this setup is that h is a Hermitian matrix. So it was quite a journey. We had lots of equal signs, but now if we stare at what we've arrived at, we have some fraction multiplied by the quantity, hv1 inner product with v2 minus hv1 inner product with v2. That's equal to 0. So all of these equalities come together to tell us that this arbitrary first eigenvector, which corresponded to lambda 1, is orthogonal to the second arbitrary eigenvector, which corresponded to lambda 2. So this is the argument that v1 and v2 are orthogonal, which means that these two eigenspaces are orthogonal to one another. So this is the full proof that any two eigenspaces of a Hermitian matrix are guaranteed to be orthogonal. So let's see this in an example. So here is an example of a real symmetric matrix, which is therefore also Hermitian. The eigenvalues of this matrix are 3 and 6. So I went ahead and I found the eigenvalues, and they are 3 and 6. Now I shouldn't be surprised that the eigenvalues of this matrix are real numbers, because this matrix is real symmetric and therefore Hermitian, and the first part of the spectral theorem applies, which says that the eigenvalues of any Hermitian matrix are real numbers. Let's take a look at the eigenspaces. The eigenspace for lambda equals 6 is spanned by the single eigenvector 1, -1, -1, and the eigenspace for lambda equals 3 is spanned by two eigenvectors 1, 0, 1 and 0, 1, -1. Let's take some inner products. So the first inner product I'm taking is the inner product of my basis vector for the eigenspace where lambda equals 6 and my first basis vector for the eigenspace where lambda equals 3. Well, this inner product equals 0. Let's look at another inner product. This is the inner product of the eigenvector as serving as my basis vector for the eigenspace where lambda equals 6 with the second basis vector of the eigenspace where lambda equals 3. That inner product is also equal to 0. And we shouldn't be surprised of this because we just proved in part 2 of the spectral theorem that any two eigenspaces of a Hermitian matrix, which again, every real symmetric matrix is also a Hermitian matrix, are guaranteed to be orthogonal to one another. So we shouldn't be surprised that the eigenvectors coming from the eigenspace where lambda equals 6 are orthogonal to the eigenvectors coming from the eigenspace where lambda equals 3. So these two calculations demonstrate that these two eigenspaces are orthogonal to one another. Again, not a surprise because this matrix is real symmetric, and therefore Hermitian, which means the second part of the spectral theorem applies here.